When a solution's made, the physical properties of that solution change. As you know, water boils at 212 degrees Fahrenheit or 100 degrees Celsius and freezes at 0 degrees Celsius or 32 degrees Fahrenheit. However, if you put a solution of salt and water onto a heater and you heat it up, it boils at a much higher temperature. If you take salt water and heat it up, it's going to boil at a much higher temperature. If you take that same solution and you try to put it in the freezer, it will freeze at a much lower temperature. Freezing point and boiling point are two physical properties of solutions that we call colligative properties. These physical properties change depending upon the amount or the number of ions of a dissolved particle in solution. And it doesn't matter what the identity of those particles are, it only matters how many of them there are. These ions, or these particles, interrupt the intermolecular forces of the solvent. And they're going to alter one of four physical properties of the solvent. The four colligative properties that you need to know for the AP exam are vapor pressure lowering, boiling point elevation, freezing point depression, and a change in osmotic pressure. And if you took baby chem, this is going to be a lot of review for you. There is some newer math, however, it's not anything particularly difficult. It's just knowing what everything is. So this video is going to specialize in vapor pressure because it's key to the other three. And then there'll probably be another video, not probably, there will be another video that does boiling point elevation, freezing point depression, and osmotic pressure. So before we plunge headlong into colligative properties, let's do a little review. In baby chem, we talked about dissociation factor. In AP chemistry, the dissociation factor is going to be called the Van't Hoff factor, and it's symbolized by the letter I. In baby chem, this was DF, and it's simply how many particles are formed when something is dissolved into the solvent. If you have a non-electrolyte, like water, and this is a really bad example because water is typically your solvent, but let's say water is your solute. If you have a non-electrolyte, non-electrolytes, again, are substances that when dissolved into solution do not conduct electricity. And therefore, it's because they do not break into any particular ions. There's no positive or negative charge. So while water is polar, it does not dissolve, it does not break up into ions, and therefore the I, or the Van't Hoff factor for any non-electrolyte, is going to be 1. So any covalent compound is going to have a Van't Hoff factor of 1. If you have an ionic compound like sodium chloride here, when it's dissolved in solution, the chlorine is going to pair up with it's going to be attracted to the positive end of water with the hydrogens. The oxygens are going to be attracted to the nitrogen, or sodium, sorry, and they're going to surround it and split up the molecule, the ionic compound. So how many do we get for every formula unit that is dissolved? Because that's what the Van't Hoff factor is. It's how many particles you get when the formula unit is dissolved. Formula unit here is sodium and chlorine, so I end up with an Van't Hoff factor of 2. What about silver dichromate? When that dissolves, the dichromate's going to be attracted to the positive end of water, so this is the hydrogens. The oxygens are going to surround the silvers, and we'll end up with a Van't Hoff factor of 1, 2, 3. In baby chem, I taught this to you as separate the metals from the non-metals and count how many you have when you balance the equation. So for any electrolytes, for ionic compounds, the Van't Hoff factor is going to be the number of particles formed when one formula unit dissolves. The experimental values of I are often different, or often less than your expected values, and this is because While sodium chloride is very soluble in water, at any given moment there can be an attraction between the sodium and the chloride that would bring them back together, and that will lower the value of I experimentally. So your expected value is going to be 2. However, experimentally you may find that it's 1.9 or 1.7, somewhere along those lines. Experimentally, the Van't Hoff factor is always less, especially in concentrated solutions. The more concentrated the solution is, the more likely a sodium and chloride ion can come closer together to be attracted to one another and form a bond. You'll have what's called ion pairing. The same can also happen for non-electrolytes, covalent bonds. Water is an awful example, but what happens in non-electrolytes is that you have intermolecular forces, LDFs, that are attracting the solute to itself, and they can form what are called dimers, which are simply when 2 units or 2 molecules of a non-electrolyte, 2 units of a covalent bond, come together and are attracted to one another. You've probably heard of monomers, which is 1 unit, or polymers, which is what most fabrics are, like, yeah, that's organic stuff. Don't worry about it. But it's called a dimer. So that's enough review of that. Let's talk about vapor pressure. For any substance, the surface of a substance is exposed to much more energy than the particles or the molecules below. The molecules at the surface can absorb sufficient energy to turn into a vapor. And those particles that finally, or those molecules that escape into being a vapor, are going to increase a pressure, exert a pressure upon the surface of whatever they came from. This pressure that they exert upon the surface is called vapor pressure. So any substance can evaporate when the surface turns into a gas. It evaporates, especially if it's a liquid. Well, not especially. If it's a liquid, it's called evaporation. And that gas, that vapor produced, exerts a pressure upon the surface of the liquid. When a solute is placed into solution, the solute will take up space on the surface of the liquid. And now on the surface of the solution, because it's evenly distributed throughout, it's going to have some of its molecules or some of its particles at the surface. And now the solvent is less exposed to the energies outside the container, and therefore less of it can evaporate off to exert a vapor pressure. So when a solute is placed into a solution, the vapor pressure decreases, and the more particles you have in that solution, the more that you will have along the surface of the solution, and the lower the vapor pressure will become. The vapor pressure of a solution is directly proportional to the mole fraction of the solvent present. If the solute ionizes the number of ions, this further affects or further lowers the vapor pressure. This is the basis of Raoult's law, where the pressure of the solution equals the mole ratio of the solvent times the pressure of the solvent at standard conditions, so at 25 degrees Celsius. The hardest part about Raoult's law is remembering that it's of the solvent, not the solute. So it's the mole fraction of the solvent. So the mole fraction of the solvent is the moles of solvent divided by the moles of solvent plus the moles of solute. But this, moles of solute, is where I comes in. You need to multiply it by the Van't Hoff factor, because for every mole of solute, you're going to end up with a particular number of particles in solution, and that is going to affect the pressure of the solution. So for non-electrolytes, you can more or less forget about it because I is going to be 1, unless they give you an experimental value of I, and then you have to plug it in and chug. If you have an electrolyte, you have an ionic compound, I is going to be different, and you need to take that into account when you solve for the pressure of the solution. Ideal solutions are solutions that obey Raoult's law, and there are no such things. Raoult's law comes very close, or solutions come very close to being ideal solutions, if they are dilute. However, when they are more concentrated, you have more particles in solution, and there are more possibilities of dimers forming. If hydrogen bonds can occur between the solute and solvent, then the vapor pressure is also going to be less than expected. This is because the hydrogen bonds will cause the attraction between the solute and solvent to be greater, and this will cause less of the solvent to evaporate and exert a vapor pressure. We call this a negative deviation from Raoult's law. An example of this would be acetone and water. Acetone and water are capable of forming hydrogen bonds, and therefore their intermolecular forces are going to be stronger when they are combined. And therefore vapor pressure will be less than what we expect. We will have a negative deviation from Raoult's law. A positive deviation from Raoult's law is one in which the vapor pressure is greater in solution than it is for each individual molecule, or for each pure substance. And this can happen when the intermolecular forces between a solute and solvent are significantly less than the pure solute or solvent. An example of this would be something that is polar, like ethanol, and something that is nonpolar, like hexene. Both of these are extremely volatile, meaning they are very easy to convert into a gas. When placed into solution together, they actually work against one another, and they will convert into a gas much easier. So the vapor pressure of this solution is actually greater than. This is a positive deviation from Raoult's law because our vapor pressure is significantly greater because both of these substances are volatile and both have very weak hexene has very weak intermolecular forces, ethanol has very strong intermolecular forces, hydrogen bonds versus LDLs. The hexene actually works against the ethanol, gets in the way of those hydrogen bonds, and they both can escape into the gas phase much easier. If a solution contains two liquids and they behave ideally, we can calculate the pressure, the total pressure of the solution, using a variation on Dalton's law, where Dalton's law is the pressure of the first plus the pressure of the second. Well, in this case, we'll be talking about the partial pressure of the first plus the partial pressure of the second. The vapor pressure of the first plus the vapor pressure of the second. And you can calculate each one of those using Raoult's law. So we could actually sub in Raoult's law for each one of these, where the mole fraction of the first times the pressure of the first at standard conditions plus the mole fraction of the second times the pressure at standard conditions of the second gas solution, or not solution, solution, and so on and so forth. Raoult's law can also be used to find the molar mass. Because you have the mole fraction of the solvent, you can find the molar mass of the solute if you solve for that mole fraction, and then from that solve for the moles of the solute. This will be assuming that I is 1, otherwise you have to take into account that there is an invisible I here in front of this n sub x. Once you have the moles of the solute, you can solve for molar mass by dividing by the mass they give you. So mass divided by moles is your molar mass. And that is Raoult's law and colligative properties in terms of vapor pressure. The next two videos will probably be, they will be, I think it might be 2. There may be 3. Maybe 1. Who knows? But coming up soon, colligative properties, boiling point elevation, freezing point depression, and osmotic pressure.